In this lecture, we're going to be talking about the psychology of forensic identification. As you know, forensic evidence is used in many trials, and forensic science is called, it's called a forensic science, a science, in which you collect, analyze, and interpret physical evidence. Now, although it seems pretty straightforward, you might ask yourself, where in this collection of words, collection, analysis, and interpretation, might psychology have a role? And if you guessed interpretation, you're correct. One of the things that has been coming to the attention of psycholegal researchers in about the past 10 years is that some of the forensic science doesn't seem to be as sciencey as we once thought. And one of the questions that psychologists have been asking is whether or not biases affect the interpretation of physical evidence at crime scenes. So let's take a little bit of a look at how forensic identification is done, what kinds of places there might be room for error, and then look at some common types of forensic evidence. So let's take a look at forensic identification. Now, many forms of forensic evidence have been used by the courts only to be abandoned when the accuracy is found to be lacking. In terms of forensic identification, what you're trying to do is link the physical evidence that's found at a crime scene to a specific individual or specific item. So just to give you an example, bullet matching evidence was widely used in the courts, but in 2004 it fell out of favor. And in fact, that technique of matching bullet evidence had been used in thousands of trials. Let me tell you what the basic premise for bullet matching evidence was. So here's the basic deal. You analyze the composition of the bullet at the crime scene, the bullet that killed the victim. And then you find a suspect, and you find that he has some bullets. And what you do is you look at the bullets in his gun. And the idea was that the chemical composition of the bullets from the same box, so in other words, if the bullets were the same, the bullets in the box and the bullets found in the victim, the chemical composition, if it was the same, that would suggest that the bullets came from the same box, because the idea was that bullets from the same box would be extremely similar in trace elements, but would be different from other boxes. But in 2004, the National Research Council published a study that showed that bullets from different boxes could have almost identical trace elements. And some of the bullets in the same box could be wildly different. And so what that did is it blew apart bullet evidence. Sometimes courts have allowed other kinds of pseudoscience evidence in the courtroom. Handwriting analysis is one, and we'll see some others as we move on. So before we get started in looking at specific evidence, let's talk about some terms that are used in this science. The first term that you see often is trace evidence. Trace evidence is evidence that was left at the crime scene. So this is the meat and potatoes of what we're going to analyze. And trace evidence includes things like fingerprints and DNA. So the suspect left that evidence at the scene of the crime. Now, the goal of the forensic examiner is to determine the source of the trace evidence. So what they will do is they'll compare the trace evidence to the suspect's fingerprint and make a determination about whether they match each other. So you have the trace evidence, and then you're trying to make a source attribution. Another term that you'll see in the forensic science literature is inclusion. Sometimes that's also called a match. What the forensic examiner says is that the DNA at the crime scene is a match for the suspect. They may even use stronger words. Sometimes they talk about individuation. What that suggests is it's not just a match. They've excluded all other sources. In other words, the trace evidence is so matched to the suspect, and in fact, it could be only the suspect that could have this kind of match. So what you're doing is you're saying it's only this person on earth who could match that trace evidence. Other terms that you'll see is excluded, and of course this is when they can't find a match between the trace evidence and the suspect. That doesn't mean the suspect necessarily is not guilty, but because the evidence could be degraded. But if you have good evidence and there's an exclusion, that means there's no match. And then finally, inconclusive. This happens when the evidence is incomplete or contaminated. And what they're basically saying is no decision can be made. One way or the other, you can't really decide whether or not there is a match. So a forensic examiner goes through this process of looking at the trace evidence, trying to figure out if there's a match, and then they have to communicate this information to the jurors. So the scientist makes the conclusion, okay, I have a match or not. And they have to communicate the nature and the certainty of their match to the judge and the jury. Now, typically there's 4 different types of ways of communicating forensic evidence. The first is a sort of a qualitative statement. This is a subjective statement saying something like, oh, the match was weak, or the match was moderate, or the match was strong. One example is forensic evidence that's given about bite marks. Forensic examiners are told to say that either the bite mark match is inconclusive, or the suspect's not the source, or it's improbable the suspect was the source, or possible that it came from the suspect, probable, and medical certainty. Now, although these words sound legitimate, there are no standards for deciding which statement to use. The degree of bite mark match is pretty subjective, and so at most you could make a qualitative statement. Another way you can communicate is just to simply say there's a match. So for example, let's say that there was a crime in which the victim's house, the way the perpetrator got into the house was by breaking a window. And let's say that there were tiny shards of glass found in the suspect or the defendant's car that match or are consistent with the glass on the broken window. So that's a simple match. The glass shards we found in the car were matched the shards from the victim's window. The only thing is that we don't really have certainty of a match, to be honest with you. For example, it would be really useful to know how common the victim's window's glass is. I mean, if you found out that 90% of the homes in America have that exact same glass, then those shards of glass mean a lot less. On the other hand, if the victim had a special kind of glass that had just been invented, during the past year or so, then that match information is much more important. Another type of communication is match plus statistics. And so this really kind of takes that simple match into you're given some certainty here. You're given the probability that this match could be wrong. So for example, just to think about it, for example, we know that red hair is less common in our population than black hair. Now, if you found red hair at the scene and it matches the defendant, that would mean more to you than knowing that the perpetrator had black hair. So knowing something about the common or uncommonness of this trace evidence is important. Unfortunately, we don't really know how common certain trace characteristics are in the population. The final type of communication is individuation, and again, like I said before, that is the most complete match to the trace. So what you're basically saying is that it requires the scientist to be able to say that the match is so detailed and perfect that the trace could only have come from one person. Okay, so that is the ultimate. So those are the ways in which you hear people talking about this. So match plus statistics might say something like, there's a 1 in 1 million chance that this is an incorrect conclusion. Individuation, probably even more so. So let's take a look at a few different types of forensic evidence. And let's start with DNA. DNA is the most objective trace evidence. And when I say objective, it means that, when we go back to that first page where we talked about collection, analysis, and interpretation, DNA covers the first two pieces, and there is very little room for interpretation. So it's probably the most objective evidence that we have. DNA was discovered in 1953, and it was first introduced into the United States courts in the trial of People versus Wesley in 1988. It's not really important for you to know that the particular case, but I think you should take note of the date, because later on when we look at the Innocence Project and we look at people who are wrongfully accused, who later are exonerated with DNA evidence, you'll see that many of them committed crimes before '88. So their DNA evidence was collected, but it wasn't used in court. Since 1988, of course, we have constructed an extremely complex database that is used by the FBI. The most common database is the CODIS. The FBI maintains this database. If DNA evidence is found at the scene of a crime, then that DNA evidence is put into this database and analyzed. So exactly what is done. Let me show you what they're doing here. This graph right here is called an electropherogram. And what it does, it shows the peaks. If you look at this, you see these peaks here at these locations. Okay? And what it does is it shows those peaks on specific locations of a gene. And what they're doing is testing the heights and the peaks of several locations on those little gene pairs to see if there's a match. If there's a match, then the conclusion is pretty straightforward. Sometimes, though, DNA tests can yield ambiguous results, and that's because sometimes the trace evidence might be of a really poor quality, or there might have been some contamination of the blood evidence or DNA evidence when it was collected. So if it wasn't collected properly, there could be some contamination. However, the analysis that's done with the DNA evidence is done by the computer, and it passes through specific algorithms, and is pretty unambiguous when there's a good match. So let's say we have a match. How is DNA evidence usually communicated to a juror? Because the calculations use a massive computerized database that also takes into account the frequency of each allele in a population, you're able to make a match plus statistics or even individuation. Almost always, DNA is communicated with a probability statement. And what the forensic examiner will usually say is something like, what are the odds? What is the probability that the match could have occurred by chance alone? So they'll often say something like the odds of the DNA from the crime scene not being from the defendant is 1 in 12 billion, let's say. And the way they do that is to do a simple probability estimate. This is something you can do mathematically, but as you're going to see, the math explodes pretty quickly, and this is something that a computer really needs to do. So if you think about two alleles, what are the odds that there's a match? It's a simple probability statement. A match or not match is like a heads or tails. The probability is 0.5. So two alleles. If two alleles matched, then you say, what's the probability that they could match even if it wasn't actually true? And that's 0.5 times 0.5. So about a quarter of the time. Okay. Now, what if there are four alleles? Figure out what you're doing now is your 0.5 times 0.5 times 0.5 times 0.5. Now, the probability that all four match gets a little tougher. 8. Again, you can see how quickly the probability that there are 8 actual matches on the DNA are pretty slim, and believe it or not, they match on many, many more than just simply 8. And so that's why you get into these probabilities of 1 in 12 billion. Usually the forensic examiner then describes this match in terms of a probability. What is the probability that this was just a random match? And this random probability then is presented to the judge or jury when the case is tried, saying things like, what are the odds that this was just a random match? The odds are 1 in a billion that this was random. And that's a pretty convincing statement for the jury. DNA evidence then is probably some of our best forensic evidence, and it's well documented and well studied. Unfortunately, sometimes in our state, there seems to be a misunderstanding. Sometimes our own state representatives don't understand the DNA match. This is the case of Andrew Johnson, and you may have heard about him. He was locked up in prison for nearly 24 years for a crime that he didn't commit. He was accused of rape. He was accused of raping a woman in Cheyenne in 1989. Note the date, right? 1989, before DNA testing was available. The victim who had been raped said she hadn't had sex with anybody for 2 weeks, and so the DNA was clearly from the rapist, from the sexual assault. Andrew Johnson was picked up, was identified, was convicted with no evidence really, except for a few circumstantial pieces. Well, 24 years later, after he had spent 24 years in prison, they decided to test the DNA evidence. And the DNA evidence showed that not only was he not the perpetrator, it actually revealed who the perpetrator was. So we're talking about individuation here. And there was a move afoot in Wyoming to provide some kind of monetary compensation for Andrew Johnson for the many years that he spent in prison. And that, it was Senate Bill 30 that was trying to go through the legislature, sorry, 2 years ago. And in fact, what happened was Representative Bob Nicholas blocked this measure that would have provided Andrew Johnson with $500,000 of compensation. And the reason that Nicholas gave for blocking that compensation was he said basically that DNA evidence alone was not enough. And he said that the DNA evidence did not prove Johnson's innocence, when in fact he was quite wrong, because it actually did. Not only did it prove that Johnson was excluded from the DNA evidence actually showed who should have been included into the evidence. So sometimes our legislators need a little bit of education themselves. I believe that this compensation is going back to the legislature next year, but I don't know if it's going to be blocked again. From what I understand, Representative Nicholas is planning to block it again. Okay, let's turn to a slightly different type of forensic evidence, one that's well known. Forensic evidence, fingerprint evidence has been with us for a very long time. In 1892, Sir Francis Galton published a book called Fingerprints that described the pattern of fingerprints. Galton argued that every print is unique and that it doesn't change over the lifespan. And he pioneered the procedure for matching fingerprints by counting points. And based on his work then, he talked the British government into adopting fingerprints as a method of establishing identification in criminal trials. So you can see, fingerprint evidence has been around for quite a long time. So what's the basics of fingerprint evidence? Here's how fingerprint evidence works. There are several patterns of fingerprints that are analyzed when fingerprint experts analyze fingerprints. And what they're doing is they're analyzing the ridges. And this ridge right here is called a loop. Loops, the swirl comes in, the ridge enters from one side and swirls and moves out the same side. You see how that works? So it moves and goes out the same side. The other one is an arch. It enters from one side, it rises, and then it exits to the other side, the arch. And of course, the whorl is a circular ridge. So those are the basic patterns of fingerprints that experts look at. How do they make an identification? Well, nowadays, the fingerprint is fed into a computer with a large fingerprint database. the computer then just goes through all of the fingerprints and then flashes when there's a match, basically. Now, one thing that you need to know, though, is that the computers don't make exact matches. What they do is they usually spit out a couple of potential matches. So based on some algorithm, these are the 4 that the computer has picked out. And then what happens is that a human examiner has to examine the fingerprints that the computer has suggested and picks out the match. So there's right here, there's a place where there's a potential for a mistake. And some errors can lead to false identifications. You're going to watch a short video this week on the Madrid bombing, in which there was a mismatch of fingerprint evidence, which led to the false arrest of somebody. Luckily, the actual person was found. But certainly, you can have false identifications because, again, once you introduce this human examiner has to make a decision, you then have the potential for error. Let's look at what fingerprint experts try to examine. Here's a set of fingerprints, and this is one in which the examiner determined that there was a match. After comparing the ridge characteristics, and you see there with the pieces characteristics that are noted to be very similar. Where the ridge is split is important, and where there are crossovers. And you can see that there are various points in this fingerprint. Now, how do they decide that, yes, I've got enough here that this is a match? Well, the criteria is kind of qualitative. They look at the print size, the shape, the orientation, and the number of similarities. You can see here that the 2 fingerprints here, side by side, there are 12 similarities. And so 12 is quite a few, and so the examiner might decide, yes, this is a match. But the decision is pretty qualitative. In Europe, it's a little bit more quantitative. So for example, many countries have specified the number of ridge characteristics that have to match in order for you to make a decision. So countries range from like 7 matches all the way to 16. So if you were in a country where you needed at least 7 matches, you would say that this exceeds that criteria, and yes, in fact, it's a match. So that is how they make those kinds of decisions. But the problem is that one of the assumptions that we've never really addressed is whether or not, in fact, every fingerprint is absolutely different. And the other thing that hasn't really been, we don't really know a lot about, is how common or rare are certain ridge characteristics. So the examiner here is honing in on this sort of swirl here. And how common is that? If 90% of the people have this sort of marking, then it's a little less interesting than to know that only 5% do. So what I'm trying to say is, although fingerprint evidence is fairly well documented, there still can be mistakes. Okay. And in fact, if you look at research on biases in fingerprint identification, it can be pretty scary. There's not a lot of research on this, but what little we know is that it's kind of disturbing in the sense that people put a lot of faith in fingerprints evidence, but the data doesn't support it. So for example, one study showed that untrained participants, when they're exposed to emotionally arousing stimuli such as graphic crime scene photos, they were more likely to say that 2 prints matched. In other words, if things are very emotional, there's this urge to find matches where none exist. Another study that was done gave fingerprint experts 8 fingerprints that they had previously seen. So in half of those, so these are experts, they're given fingerprints that they've already made a decision about. Half of the ones that they were given, they had declared as a match, and half they had declared as non-matches. So pretty clear, they made a decision. Half of these fingerprints were easy to judge, and half were difficult. So they picked some difficult fingerprints and some easy fingerprints. And then half were given misleading information about the particular print, saying that the suspect had confessed. And so they were simply asked to look at these fingerprints and then tell us whether there was a match or not. And the results were this. Only 1/3 of the examiners were perfectly consistent in their judgments. In other words, they said to these 8 fingerprints exactly what they had said before. So 2/3 of the examiners gave you inconsistent results. And where the changes came in, the changes in judgments were most likely to occur with the difficult fingerprints, which makes sense, and also when they were told that the suspect had confessed. So you see, knowing that the suspect had confessed biased their decision making on the task. And so we need a lot more information about fingerprint identification and the kinds of variables that might lead to biases in identification. Okay, we've talked about the 2 most common types of forensic identification, but there are also others that we either don't know whether it's valid or where the data is very weak. So for example, bullet striations, something that's still used in courtrooms today. There are no standards for how large the striations, how many types of matches must be present in order to say, yes, there's a match. We just simply put our faith in the examiner. Another technique of weak validity actually is bite mark matching. Very little data on the validity of this kind of testimony. Tools, whether this tool was a tool that was also at the crime scene, matching a tool to the crime scene so that I could say that this knife that was in your kitchen is the tool that killed the victim. Those kinds of decisions and matches are being made in the courtrooms today, but there's not a lot of evidence that is not heavily influenced by interpretation. Okay, now this was just a short little preview of forensic evidence, but I hope it gives you a better understanding of how forensic evidence is used and the fact that there is a lot of interpretation and bias even in something that seems to be pretty cut